Vipul Goyal, who's going to talk to us about unclonable secret sharing.
Okay, great. Thank you. So I will talk about a new primitive called unclonable secret sharing. This is joined to work with Prabhanjan, Jiahui, and Chipan. Okay. So to start with, for some motivation, let's say we have Alice. She has some super secret data S, which she wants to store somewhere, maybe temporarily, maybe for a long time. So what she decides, maybe she decides to hire a few different servers. You can think of them as cloud servers, maybe one of them is Microsoft, AWS, and so on. So she can just secret share the data and maybe store one share with each server, right? So she can secret share SH1 to SHN, and it goes and it gets stored across n different servers, assuming that the servers don't collude, servers don't know what the secret is. She can even ask the servers to delete all the data, the transaction is complete. But the obvious problem is that if the servers are somewhat malicious, they can continue storing the data, right? They don't have to delete, and we all know how hard it is to compel big companies to delete any kind of data. They are all data hungry, right? And then at a later point, maybe after a year, maybe even after 10 years, some adversary comes along, adversary is interested in the data by Alice, and adversary says, hey, let me pay the servers and I can buy the shares. And if the adversary is able to talk to sufficient number of servers, adversary can recover the data even after a long time, right? So this is a problem. And the question is, can we do anything in this setting? What can we do? Well, the problem is, servers can always keep a copy of the share, return a copy to Alice, keep another copy. There's not much you can hope to do here. So this is a problem which has been recognized. It has even been studied in the classical setting. And there is a primitive called traceable secret sharing, which is directed towards the study of this problem. And traceable secret sharing does not stop this problem. It only acts as a deterrent. So what it means is that if the servers continue to store the data, let's say give it to an adversary later on, then essentially the server is sort of giving a cryptographic proof of fraud, of cheating. And if Alice gets her hand on that, Alice can potentially sue the servers in a court for breach of contract and whatever, claim damages and so on. So traceable secret sharing gives you some kind of deterrence against this type of attack, but it doesn't prevent the attack as such. So what can we do? In particular, the focus of this talk will be on the quantum setting. Is there anything we can do in the quantum setting, anything better than what we can do classically? And the hope for why we might be able to do better in the quantum setting comes from the famous no cloning theorem, right? So the issue was servers were able to clone the share and keep a copy, but in the quantum setting, maybe we can prevent something like that. So there's a no cloning theorem which says that there's an unknown quantum state. Let's say you want to design a cloning machine to create 2 copies of this state. No cloning theorem says that in general, this is impossible. And we have to be a bit careful here. No cloning theorem says that there exist some states for which this is impossible, right? So it doesn't hold for any arbitrary state, so you have to be careful, you have to give security proofs carefully. And no cloning theorem has given rise to this really beautiful line of research. We are able to build primitives which we can only imagine classically, but they are clearly impossible. It all started with the introduction of quantum money in 1960s. When we think about quantum cryptography, the first thing which comes to mind is quantum key exchange. But quantum money actually even predates quantum key exchange. And quantum money is like some quantum states which can serve as tokens or coins. You can even verify them offline. You don't need to connect to any blockchain or any server or anything like that. You can verify them offline, and yet you cannot make 2 copies of a coin. So something very useful, very sort of analogous to the banknotes which we have in circulation. A lot of work on quantum money, then there's some work on quantum copy protection where maybe there's a software vendor which creates a program, maybe sells you the program. Quantum copy protection guarantees that you cannot create 2 copies of the program and then maybe further sell one of the copies. There's unclonable encryption, decryption. We are designing cryptographic primitives where maybe the ciphertext cannot be cloned, or where maybe the keys cannot be cloned, and so on. There's this line of research on certified deletion, where I give you some data, I can force you to delete it, and you can give me a proof that you deleted the data. Again, impossible in the classical setting, because I can always clone the data. There's this recent work on unbounded leakage resilience, where maybe you have a secret key, adversary can break in and can download arbitrary information about the secret key, and still the secret key remains secure, you cannot decrypt, as long as all the leakage is classical. So all of these things are made possible using this beautiful no cloning theorem, very useful in cryptography, and sort of the goal in our paper is to continue the study of this notion of unclonability and generalize it to secret sharing. So unclonable secret sharing, to our knowledge, it has never been considered in the literature. A very natural primitive, it can prevent the cloud servers from copying your data. So the question is, can we define unclonable secret sharing? Can we achieve it? And so on. So here's the outline for rest of the talk. We will try to define unclonable secret sharing. We will see a few different definitions. Some of them will turn out to be possible, some of them will be impossible. We will study connections to what is known as unclonable encryption and position-based cryptography or position verification. I will talk about these things. I'll talk about positive results, negative results, and then there's a lot of different open problems. Okay, so let's try to define unclonable secret sharing for the most basic setting of just 2 parties, right? So just the syntax first. So there's a sharing algorithm which takes as input a secret S. This secret can be a classical secret, it can be a quantum secret, it doesn't matter. This algorithm outputs 2 shares. Let's call them row 1 and row 2. These shares typically would be quantum to enable no copying or no cloning. And then let's say you can go ahead and you can store these 2 servers, 2 secrets across 2 different servers. So row 1 and row 2, and these servers, they don't talk to each other. And then at a later point, let's say Alice can go ahead, can retrieve these 2 shares, row 1 and row 2, can apply the reconstruction algorithm to recover the original secret, S. So this is the syntax. What do we want from the security of this primitive, right? So yeah, so you have 2 different shares, row 1 and row 2. So in the security game, we now consider 2 different entities. We can call them Bob and Charlie. They are both interested in reconstructing the secret and recovering the secret, okay? So, so the servers can try to potentially, and the servers are adversarial here, they don't talk to each other, but they can do whatever they want otherwise. They can try to clone the share in any arbitrary way. So server 1, which has row 1, can try to clone it into sigma 1 1, sigma 1 2, send one of the copies to the first reconstructor, the second copy to the second reconstructor, and server 2 again clones, does something analogous, and the 2 parties, Bob and Charlie, they try to output the secret S. So both of them, they try to reconstruct. And what we want is that this should not be possible, right? There should not exist 2 such reconstruction algorithms and adversarial strategy which allows you to sort of clone in this way. And in fact, this is just the basic definition. We want something even stronger. You cannot even distinguish the secret S from uniform. So all partial information about the secret is hidden for at least one of the reconstruction algorithms. Okay, we can naturally generalize this to n parties as well. So here we have like n different servers, none of them talk to each other. All of them get a share, and then still there are two algorithms which are trying to reconstruct, and at least one of them should fail to reconstruct. We can even talk about collusions between the servers. We can generalize, make it stronger. Maybe there are t different servers, they all collude with each other, but t is not large enough to reconstruct the secret. So even in that case, we might want security. They should not be able to support two different reconstruction algorithms. Okay, so unclonable secret sharing, apart from this unclonable security, also satisfies the regular secret sharing security, which is that, you know, if you have n-1 shares, you shouldn't be able to reconstruct. You shouldn't be able to recover even a single copy of the secret. And then there's, of course, the unclonable security, which I already talked about, which is that the servers cannot clone shares. We can study this primitive in the computational setting or in the information theoretic setting, and we will try to do both in our paper. Another important thing, actually turns out to be very important in this setting, is entanglement, right? Are the different servers entangled with each other or not? So even the servers which don't communicate with each other, they might be entangled with each other. And then achieving security becomes more tricky, because we know that in the presence of entanglement, many tasks which were hard before, actually they become easy. And an example of this is the classical CHSH game, which entangled parties can win, but non-entangled, non-communicating parties cannot win, right? Yeah, so we can consider some subset of the servers being entangled with each other. We can still ask for this unclonable security in that case. So how much the entanglement is, to what extent, that turns out to be important. We can even consider like different subsets which are entangled with each other. We can consider entanglement graphs. So what we can do is we can divide the parties into disjoint connected components. Within each component, they don't communicate with each other, but they can share entanglement. Okay, so this gives rise to what we call USS1, USS2, USSK. What does USSK mean? It means that there are k disjoint components. Within each component there is entanglement, but not from one component to the other component. Okay. And naturally, the fewer components there are, that means there's more entanglement, right? So more secure the security definition is, but then it's also harder to achieve. So USSK is easier to achieve when k is larger, because that means that there are more components with no entanglement across components. It means overall there is like less entanglement, which we can try to exploit. And USS1 is, of course, the most challenging setting, because then any party can be entangled with any other party in any arbitrary way. And here's a trivial implication that USS1 implies USS2, and so on. Okay? So now we will talk about constructing USS1, USS2, and so on, but let's pause for a moment and let's look at connections to other primitives. So there's unclonable encryption, right? So in unclonable encryption, there's a ciphertext, an encryption of the message M, and Alice tries to clone this ciphertext into, let's say, two parts, row 1 and row 2. They can go to Bob and Charlie, and then the decryption key is given to both the parties. The decryption key, you can think of it as classical, and then both these parties try to output the message M. So they try to decrypt the message. And unclonable encryption says that this should be impossible. You cannot clone the ciphertext like that. So naturally you can see it seems like clearly connected to unclonable secret sharing. So it turns out that unclonable encryption actually implies 2 out of 2 USS2. USS2 means there are 2 parties, really no entanglement, 2 different components, 1 party in each component. And yeah, this follows a simple reduction. The ciphertext and the key in unclonable encryption, they become 2 different shares. So that sort of gives you unclonable secret sharing. But on the other hand, if you go to USS1, which is a stronger primitive, it turns out that it implies unclonable encryption. Okay, so unclonable encryption can be thought of as lying somewhere between USS1 and USS2. Another application or sort of the connection of this notion is to quantum position verification. So what is position verification? So here, we are thinking about just 1 dimension. You can consider this notion in higher dimensions as well. Here there's a prover, there's a line, prover is located somewhere on the line. Then there are 2 different verifiers. The prover is trying to prove to the verifier that it's, let's say, at the location 0.5. It's exactly at the middle of this line. So this has been a problem which is well studied over the last 10 years. How can we design quantum position verification protocols and so on? It turns out that USS1 implies this position verification, and why? Here is sort of a simple protocol. The 2 shares of USS1 can be sent to the prover, and the prover can try to reconstruct, give back the secret. So why does this work? Well, the typical attack in this setting is that instead of a single adversary being present in the middle, we can think about like 2 different adversaries, one close to verifier 1, another close to verifier 2, and they can end up convincing the 2 verifiers. But because now only one of them can reconstruct the secret S, 2 different adversaries in this way can no longer exist, because that would require cloning essentially. Okay? Okay, so now let me go to the first positive result. It's one of the main results in the paper. It says that if k is high enough, so omega log n, then unclonable secret sharing, even information theoretically secure, turns out to be possible. Okay? And the starting point of our construction is what is known as BB84 states. So BB84 states is this x in the basis theta. What it means, just think about 1 bit. If theta is 0, then x is encoded in the computational basis. If theta is 1, x is encoded in the Hadamard basis, right? So x is a string which is encoded according to the basis defined by theta. If you don't know what theta is, then it's hard to clone this state. So Alice gets this x to the theta, tries to clone it, row 1 and row 2. Bob and Charlie, they don't communicate with each other, and then both of them get the basis theta later on, and they try to guess what x is. And there are monogamy of entanglement theorems from the literature which say that such Alice, Bob and Charlie, they cannot exist. So this already seems like very close to what we want, unclonable secret sharing. So here's a naive idea. Does this already sort of give you a starting point for unclonable secret sharing? Maybe x to the theta and theta will be the 2 shares, right? You cannot clone x to the theta, so you cannot clone at least one of the shares. So at least one of the reconstructors will fail. Turns out that this is somewhat of a progress, but not quite. This is because even though Bob and Charlie cannot output x as it is, it turns out that it might be easy for them to output some partial information about x. It turns out that they can guess, in fact, each bit of x with probability at least 3/4, even higher. So what we need is, we need to sort of amplify this hardness, right? It's hard to guess 1 bit, but not close to half. Probability is like 3/4. So our idea is that we try to use a parallel repetition of many of these BB84 states. We will try to XOR all of these secrets together, and we will hope to amplify in that way. Okay, so here is our construction idea, just the basic high level idea. The share algorithm picks n-1 BB84 states, where you can think of n as related to the security parameter. There are n-1 BB84 states. Then the last, those are the n-1 shares. Then the last share is basically all the thetas for all of these states. Okay, so the reconstruction algorithm, if it has the last share, it knows all the bases. It can recover all the x1 to xn-1. Then it can recover the message m by XORing all of these together. Okay, and this turns out to be the main technical contribution of the paper, that this XORing the different BB84 states actually makes each bit maximally unpredictable. You can only predict with probability half plus negligible, not more than that. Okay, then we also have a construction for USS1, which is the best you can hope for, but it's in the quantum random oracle model. So we show that unclonable encryption plus quantum random oracle model implies USS1. And yeah, maybe let me skip the high level idea. And then we have 2 different negative results. The first one actually says that USS1 unconditionally in the information theoretic setting is actually just impossible. Kind of surprising. If all the parties have unbounded entanglement and unbounded memory resources, USS1 is impossible, and the general attack uses what is known as port-based teleportation plus standard teleportation attacks to exploit entanglement. Then there's the final negative result, which is even in the computational setting, there are some barriers to getting USS1. And we show that there's a lower bound on the number of gates for the reconstruction circuit, number of T gates. So maybe it's possible, but at least there are some barriers to overcome. Okay? So the conclusion is, yeah, we introduced this natural primitive of unclonable secret sharing. There's unclonable encryption, commitment, NISIC, so it adds to this this array of primitives. It has natural connections to encryption and position verification. And the key open problem is building USS1 in the computational setting, or even USSC for any constant C. Okay, that's all.
All right, thanks a lot, Vipul. I think we have time for one quick question while Alex gets ready. Does anybody have a question?
Yeah.
Thanks for nice talk. I have a question on construction of USS. You seem to construct USS in the quantum random oracle model, but you don't. So do you have any idea to construct USS in the prime model, for example, from the hardness of LWE?
Yeah, that's an open problem. So unconditionally, it's impossible as we showed, but in the computational setting, without random oracle, that might be possible, and that's the main open problem essentially.
Oh yeah, thanks.
Any other quick questions? We have 1 minute. If not, I'll ask a question.
Yeah.
Can you generalize this to like Boolean formulas instead of just K out of n thresholds?
Yeah, that's a good question. In fact, we didn't even talk about threshold, it's just n out of n. I think generalizing to threshold is not that hard, but yeah, to more advanced access structures like Boolean formula and all that, we didn't really think about it.
Awesome. Well, let's thank Vipul again. Thank you very much, Vipul. All right, thank you, everybody. Our next talk is going to be by Alex, and he's going to talk about generalized hybrid search with applications to blockchain and hash function security. Take it away, Alex.
Yeah, thank you so much. So yeah, this is, in this presentation, I'm going to talk about our work on generalized hybrid search with applications to blockchain and hash function security. And this is a joint work with my amazing collaborators, Swan Garai and Fang Song. So in this talk, we are going to focus on quantum query algorithms. Why are they important? Well, firstly, from an algorithmic perspective, as we know, many of the known quantum algorithms, they are in fact query algorithms. And secondly, they allow establishing lower bounds on the number of resources required to solve a particular problem. And thirdly, from a more practical point of view, if one is able to find an efficient query algorithm together with a circuit that implements that oracle, that is going to lead to efficient algorithms for explicit computational problems. But perhaps more importantly, query algorithms play a crucial role from a cryptographic perspective, because as we know, studying the query complexity of certain problems tells us the post-quantum security of different crypto systems. So in this talk, we are going to work in this query model, which you can think of it as an abstraction that is widely used in both cryptography and complexity theory. And the most famous example is the random oracle, in which several crypto systems are designed and analyzed. And in this model, we are saying that a query algorithm is trying to solve a particular problem by querying a black box function f. And the complexity of this algorithm is given by the number of queries performed to this black box function. However, quantum computing is bringing a new query model, the quantum random oracle, in which now superposition queries to this black box function f are allowed. And as a result, this is going to equip quantum parties and quantum algorithms with stronger capabilities. So the landscape of quantum cryptography in this query model can be divided into two main categories. So on one hand, we can think of the design of new cryptographic applications in which all parties can perform quantum queries to this random oracle. And the second main direction, which is also the one that we are going to focus on today, is the study of post-quantum security of protocols that were known to be secure in the classical world, in the classical random oracle. So our task is to analyze if these protocols remain secure and how secure they are when the adversary is equipped with these stronger quantum superposition queries. So in this talk, we are going to focus on a particular subclass of query algorithms, which are known as the hybrid quantum classical query algorithms. And these are motivated by the fact that it is to the interest of every party to supplement quantum with classical computational power. And this corresponds to the reality that in general entities that have quantum computers, and you can think of like big companies or government agencies, they also coincide with those that can employ high performance computing, such as clusters and supercomputers. And this reality inspires this theoretical hybrid query model, in which one is granted a quota of classical and quantum query. And of course, this is a generalized model that subsumes both the classical and the quantum query models. And as we mentioned, one of the main implications of query complexity is in the study of post-quantum security of crypto systems, namely revisiting whether these classical protocols remain secure against quantum adversaries. And one very notable example is Bitcoin, which, as you all know, it's the first and most popular decentralized cryptocurrency. And the Bitcoin backbone protocol by Garai et al. Is an abstraction that formally studies the security of the Bitcoin. And the security is studied in the random oracle. And in this seminal work, they have shown that the protocol remains secure against classical adversaries in the random oracle. And the basis of the security proof lies this concept of proof of work, in which at a very high level, parties prove that they spend some computational resources. And hence, we would like to, for the post-quantum security, we would like to revisit its security and understand how it's going to change when the adversary is equipped with a quantum computer. However, in order to study post-quantum security, as you all know, typically a significant effort needs to be involved in order to deal with these quantum query adversaries. So what this means is that in order to maintain security against these quantum attackers, one needs to pay a high efficiency overhead. And this can come in requiring other more complex constructions from our crypto systems or larger key sizes. And as we all know, the threat of quantum adversaries is indeed alarming. But on the other hand, these quantum attackers against these crypto systems, they typically need to run large-scale quantum computations coherently for a very long time. And we also know the reality that quantum devices available in the near-term future, they are likely to be both computationally restricted as well as expensive. So therefore, we believe it is of high importance to study security against hybrid adversaries, because this would actually give us more accurate security parameters, more optimized parameters, depending on the actual resources that are going to be available to these near-term quantum adversaries. And as a result, we believe it is crucial to also additionally study the post-quantum hybrid security of these crypto systems. And this is what we are focusing in our work. In particularly, we are trying to examine the hardness of various search problems against hybrid strategies. And more precisely a bit, our focus is on a class of general search problems that can have multiple solutions and in which the input is sampled according to an arbitrary distribution D. And for this class of general problems, we aim to establish their hybrid quantum classical query complexity, so the hardness against these hybrid adversaries. And then it turns out that by choosing appropriately for this input distribution D, such as the Bernoulli distribution, this turns out to have several interesting cryptographic applications. So at a high level, our work extends the seminal work of Rosmanis in 2022 that proposed this hybrid query model. And in this hybrid query model, he studied the hardness of a more basic version of the search problem, which only allows for a single solution and which is only uniformly sampled. And concurrently, Hamoudi, Liu, and Sina in 2002 proposed the recording technique as a method to deal with the hardness against hybrid adversaries. And in this model, they studied the hardness of collision finding. And now I just want to very briefly mention some cryptographic applications that result directly from our hardness result against that family of search problems. So on one hand, we can generalize the security of the Bitcoin protocol from a setting in which the adversary is fully quantum to a setting in which the adversary can now have both quantum and classical capabilities. Secondly, we can re-examine the generic security of hash functions, namely properties such as one-wayness, second pre-image resistance, or collision resistance against quantum classical hybrid adversaries. And as a more general future direction, as we all know that security definitions, they often have a component that is given as an oracle. And a long line of research in post-quantum cryptography focuses on setting the right definitions and constructions to deal with these adversaries that have now quantum access to this oracle. And we believe that it would be of high importance to extend this long line of research to the hybrid landscape, because as mentioned, this would give us more fine-grained security assessments for the post-quantum security of crypto systems. So in particular, our first result is a hardness result that, as mentioned, studies the query complexity of this distributional search problem, which can be summarized as follows. So given a function f, a Boolean function f, sampled from an arbitrary distribution D, the task is to find the preimage of 1 given only a black box access to this function. And our hardness result says that for any algorithm that is equipped with C classical queries and Q quantum queries, the maximum success probability to solve this problem is going to be the square root of the number of classical queries plus the number of quantum queries, everything squared, multiplied by nu D. Where this nu D, you can think of it as just the average fraction of solutions, where the average is taken over this distribution D. So looking again a bit more on this hardness statement, we notice that for this nu D, that basically captures the, as mentioned, the average fraction of solutions, this only depends on the distribution, on the input distribution, and in particular, it has no dependency on the algorithm. So in order to apply our hardness result, the only thing one needs to do is just to analyze this nu D quantity, which can typically be done by some standard combinatorial argument. And now I just want to mention like a few examples. So for instance, think of the problem in which we have a single marked item and in which the function f is sampled uniformly at random. Then the average fraction of solution is just going to be 1 over the size of the input space. Similarly, if now we know that our function has W preimages of 1, then the average fraction of solution is just going to be W over the size of the input. And finally, if the function is sampled according to a Bernoulli distribution, meaning that every input is going to be set to value 1 with some probability eta, then the average fraction of solution is going to be again this eta, which tells us the maximum success probability to solve this problem. So now I just want to very briefly mention a bit about how we show this hardness. So essentially, to set the framework, we are going to think instead of like an adversary that needs to distinguish between two cases. So in the first case, it's going to have access to a Boolean function f, sampled from the distribution D. And in the second case, it's going to have oracle access to this constant zero function. And what one needs to do is to argue that a single query is going to diverge the state of the algorithm in the two cases by some small amount. And this small amount is known as a progress measure. And now, to find the single marked item, then one is to argue that the final states are going to differ significantly. And in particularly, this means that sufficiently many queries are necessary for the progress to grow properly. But one is immediately notices an issue, because when classical queries are now mixed with quantum queries, the quantum states is going to collapse after each classical query. And as a result, it becomes unclear on how to measure the progress. So to deal with this, then Rosmanis had this very nice idea of like replacing classical queries with what is known as a pseudo-classical query. So more precisely, to define this pseudo-classical query, we can first position classical and quantum queries within the same model. So you can think of a quantum query as just a map that is going to map superposition over all x to a superposition of x f of x. And then a classical query is just going to be the result of measuring the input register that is going to give us a single x and the corresponding f of x. And then a pseudo-classical query is going to do something similar, but instead of measuring the input, we are going to measure the output register. And what this gives us is that we are going to get one out of two outcomes. Because the function is Boolean, this means that we either get the superposition over all the preimages of 0 or the superposition of all the preimages of 1. And we call the first the zero outcome branch, and the second case the one outcome branch. And now it becomes clear that if we replace classical queries with pseudo-classical queries, then one is to just track progress between the following two situations. So in the first case, we have the zero outcome branch, when f is sampled from distribution D. And the second case is the state in the case that the algorithm has access to this constant zero function, which of course is always going to stay in the zero outcome branch. And you can see that this is the case because, of course, if the result of a pseudo-classical query is going to result in the measurement outcome 1, then you can immediately distinguish between the two cases because the zero outcome function, the old zero function is never going to give you the answer 1. And then it becomes quite clear that the algorithm to distinguish between the two is only going to fail if the state is going to stay in the zero outcome branch. So namely is going to have a pseudo-classical query resulting in the measurement outcome 0, and still is going to be close to the state in the constant zero case. Because this means that the states of the algorithms are very close, so the algorithm cannot distinguish between the two situations. Our second main result is actually constructing an algorithm for this problem. So in the first part, we have shown the hardness of solving this distributional search problem. And in the second case, we also want to show, okay, can we construct an algorithm that gets close to these upper bounds? And the algorithm idea is actually very simple. The algorithm is going to first spend all these classical queries, and then it's going to spend the quantum queries in a modified Grover. And then we want to analyze the success probability of the algorithm for different distributions D. And we can even show optimality for special cases, namely for uniform and Bernoulli distribution situations. So our starting point is actually to first see how to use the quantum queries for these distributional search problems. And the idea is to start from like Grover's algorithm and adapt it in such a way that is going to be tailored to this prior distribution, to this prior knowledge we know on the distribution D. And more precisely, for every input x, you can think of the function omega that tells you what is the likelihood that that x is going to be a solution for the search problem under distribution D. So in other words, what is the likelihood that f of x is going to be equal to 1 under distribution D for any input x? And this is actually going to be the main distinction from like a standard Grover. In a standard Grover, we will start with a uniform superposition, while here our initial quantum state is going to be a state in which the amplitudes for every input is going to be given by these weights omega of x. And just as a small remark, we notice that while computing this omega of x from the description of D might not be time efficient, this is still fine because we only care about the query complexity of our algorithm. So this is the modified algorithm. So as mentioned, the main distinction is that we notice here that for this phi 0 state, this initial superposition is going to be a superposition state in which for every input x, the amplitude is given by this omega of x. So the amplitude of every input is going to be given by the likelihood of that input being a solution for the distribution search problem. And then we are going to just apply modified Grover iterations. What do I mean by modified Grover iteration? Well, we apply two reflections. One on the initial superposition state, which is this phi 0 state, and then the other one, which is a reflection around the solution subspace, which is going to spend exactly one quantum query to the function f. And now with these pieces, we can just describe our full hybrid algorithm. So as mentioned, in the first stage of the algorithm, we are going to spend all the classical queries. And more precisely, we can gather in this set S all the inputs that have the highest likelihood of being a solution under the distribution D. And now, if after spending all the classical queries on querying this set S, if no solution is found, then we are going to run the quantum algorithm, but of course on the reduced search space. So once we have eliminated these points in the set S from the total search space. Now, in other words, we are going to invoke the previous quantum algorithm in a modular fashion. And the final piece is actually just to show that the success probability of our hybrid algorithm is given exactly by just the average of the success probability of the classical stage and the success probability of the quantum stage of the algorithm. And with this, I would like to conclude by also just mentioning some interesting future directions. So regarding the algorithm, we would also like to show the optimality of our classical algorithm that first is going to query the inputs with the highest likelihood, and also the optimality of our hybrid algorithm. Because as mentioned, we are only able to show that it is optimal with respect to the uniform and the Bernoulli distributions. Secondly, we'd also like to find problems, not necessarily like search problems, but for which the success probability of a hybrid algorithm is not just going to be like the success probability of solving that problem with classical queries and the success probability of solving that problem with quantum queries. And finally, from a more cryptographic perspective and a more general direction, it would be very nice to continue this study and analyze post-quantum hybrid security of other crypto systems that can include digital signatures, encryptions, or commitments. Thank you.
Thanks a lot, Alex. Do we have any questions? I'll ask a question then. Could you comment on some of the difficulties in, say, extending this to something like, symmetric key encryption?
So basically, it's just that our current harness framework is more tailored for like search problems. And in general, there is like only one other framework that I mentioned. That is, you can think of it as a sort of like recording technique tailored to the hybrid algorithms. But in general, just a bit tedious to work with them. So it was just that you would have to kind of like really analyze the hardness of those problems in these query models, and probably like a lot of work would have to be involved into showing these.
Okay, even for something like signatures, where it's like fundamentally a search problem, sort of?
Yeah, so for like, if you can reduce it to like a more basic version of like a search problems, then yeah, I think you can use directly our framework for that. But it really depends on the crypto system that you are trying to look at, yeah.
Cool, thanks a lot. Does anybody want to ask a last second question? No? All right, well, let's thank Alex again. Thank you for a nice talk, Alex. All right, our final speaker of the session is Shoko Yamada, and he'll be talking about quantum unpredictability. Take it away. Thank you.
Thank you for introduction. Today I will talk about quantum unpredictability. This is a joint work with Tomoyuki Morima and Takashi Yamakawa. First, I will talk about pseudo-randomness and relationship pseudo-randomness and unpredictability in classical world. So in classical cryptography, pseudo-randomness and unpredictability are both useful to construct cryptographic primitives. So pseudo-randomness is formalized as a pseudo-random function, and from there we can construct many cryptographic primitives. For example, zero knowledge proof, bit commitment, message authentication codes, and SKE. Also, unpredictability is formalized as unpredictable function. I will explain it later. Roughly speaking, it is almost a pseudo-random function. So it is the ensemble function labeled by secret key K. As a security, its function, no efficient adversary cannot predict the output of its function. From this unpredictable function, we can construct these primitives. And also, in the classical world, unpredictable function is equivalent to be pseudo-random functions. In the quantum world, pseudo-randomness is also useful. So there are many quantum analogs of pseudo-random function. So one of them, today I will focus on pseudo-random function-like state generators. I will call it PRFSG for short. This is a quantum algorithm on input secret key K and X, output quantum state phi K of X. As a security, roughly speaking, if adversary does not know this secret key K, each of the output look like independent, truly uniform random quantum state. So the reason we consider this PRFSGs is we can construct many primitives from this. We can construct many primitives from these PRFSGs. For example, SKE, unclonable MAC, and bit commitment, and so on. So this figure captures the relationship PRFSGs and many primitives. So from PRFSG, we can construct these primitives: zero knowledge proof, MAC with unclonable tag, bit commitment, and SKE. But unpredictability in quantum world does not studied before. So what is the unpredictability is the quantum world. So the second question is it equivalent to quantum randomness, for example, PRFSGs? So and also we have some question about can we construct cryptographic primitives from the quantum analog of unpredictable functions? Based on this motivation, we introduce unpredictable state generators as a quantum analog of unpredictable functions. I will call it UPSGs for short. And also from UPSG, we construct into CPA SKE and EUF CMA MAC with unclonable tag. From them, we can construct all primitives implied by PRFSGs. And also, we show BQP is not PP is necessary for the existence of UPSGs. But for the time, we don't have, I don't have enough time, so I will omit this in this talk. So this figure captures our result. So, but trivially, we can show PRFSGs implies UPSGs. But the opposite direction is not clear. However, we can construct all non-primitives implied by PRFSCs from UPSGs. So therefore, we can say for quantum cryptography, unpredictability is sufficient. So this is the main message of our talk. So let's consider a definition of UPSGs. Before talking about it, I will start from unpredictable functions. So unpredictable function is a function efficient. It is developed by K. So as a security, let us consider the following security game. So first, adversary queries. First, challengers samples secret key K. Then adversary queries many bit string X. And then challenger returns its output Fk of X to adversary. And at last, adversary outputs a pair of bit string X star and Y star. Here, X star should not be created in the first stage. So as a security, we require this inequality. So the probability Fk of X is equal to Y star is negligible. So this captures unpredictability of this function. As a UPSD, we consider the output state is a quantum state of phi k of X. So the security game is almost similar, but for each query, challenger returns the quantum state phi k of X to adversary. And then adversary output a pair of bit string X and quantum state rho. Here, X star should not be created in the first learning phase. So for this rho, we require this inequality. So this inequality says this output quantum state rho is very far from phi k of X. So this captures unpredictability in the quantum world. Next, I will talk about how to construct SKE from UPSGs. So without robless generality, we can consider int CP_SKE for single bit messages. So if we can construct SKE for single bit messages, we can construct SKE for many bit messages by encrypting each message one by one. So for this case, security game is the following. So first, adversary queries a message M, and then challenger returns its ciphertext. And then challenger chooses some bit B. Then challenger sends its ciphertext to adversaries. So the adversary answers its ciphertext is with B equals 0 or B equals 1 or none. So as a security, as a security, no efficient adversary cannot distinguish its ciphertext is correct B equals 0 or B equals 1. So our construction of SKE from UPSG is the following one. So first, in the encryption algorithms, chooses random bit string X and Y uniformly random. And let phi k of X be a UPSGs. Then ciphertext is a pair of X, Y, and the superposition of phi k of X plus -1 to B phi k of Y. So in other words, the messages is encrypted this relative phase. So for security proof, our goal is to show this CT0 is indistinguishable from CT1 if adversary does not secret key K. So to show this, we use the following theorem. This theorem says distinguish phi k of X plus phi k of Y from phi k of X minus phi k of Y is as hard as converting phi k of y into phi k of x. So in other words, if adversary cannot construct phi k of x from phi k of y, he cannot distinguish phi k of x plus phi k of y from phi k of x minus phi k of y. So here, this phi k of x is UPSG. So from the unpredictability, adversary cannot create a phi k of x even if he has a phi k of y. So therefore, by combining the security of UPSG and this theorem, we can say the adversary cannot distinguish CT0 from CT1. Next, I will talk about MAC with unclonable tags from UPSGs. So, unclonable MAC is a MAC which tag state is unclonable. So first, adversary can query many messages X, and then challenger returns the tag state tau kx. Here we consider this tag state is a quantum state. And then adversary choose some X star. Here this is not queried as before. Then challenger returns the valid tag state tau kx star. And then by using this, adversaries output some quantum state row. Here, as a security, we require this row is far from the 2 copy of tau k of x stars. So therefore, this adversary cannot clone valid tag state. So here I remark the following. So standard EU FCMS security is implied this unclonability. So therefore, it suffices to construct a MAC which satisfies this unclonability. So let's go construction from UPSGs. So the main technical issue is how do we make tag states unclonable. So as a UPSG, we require its state is unpredictable, but we don't require it is an unclonable state. So the idea is a BB84 state and SKE. So let enc be encryption algorithms of SKE, and K is a pair of K dash and K dash dash. So our construction is the following. Here, Y, Z, theta is a random bit string. The first one is, first P theta is a random Pauli labeled by theta. And this phi K dash X, Y, Z is the output of UPSGs. So therefore, the first component is first we generate a UPSG and then apply a random Pauli labeled by theta. And the second component is a BB84 state by labeled Y and Z. And then last component is a ciphertext for Y, Z, theta. So for the unclonability, proof of unclonability is very simple. So here adversary does not know this secret key K dash and K dash dash. First, this ciphertext is the last component is indistinguishable the ciphertext for all 0 messages because the security of SKE. Next, by using the property of random Pauli, so the first component is perfectly indistinguishable from Machimari mixed state. Then the adversary state is indistinguishable from this state. And here YZ is a BB84 state. So therefore, from the property of BB84 state, this state is unclonable. So therefore, we can say our construction satisfies unclonability. So let's summarize my talk, and I will mention about some open problems. As a summary, we formalize UPSGs as a quantum analog of unpredictable functions. And then we show all non-primitive implied by PRFSGs are also implied UPSGs. For constructing, so therefore, we can say for constructing cryptographic primitives, unpredictability is sufficient in the quantum world. And so, as an open problem, I will remark some open problem. So here we show PRFSGs implied UPSGs, but its opposite direction is not clear, despite in the classical world its direction is 2. So therefore, can we separate UPSGs from other pseudo-random primitives in the quantum world? For example, PRFSGs and pseudo-random state generator or pseudo-random unitaries. And also, can we find the primitives implied by PRFSGs but not implied UPSGs? If we can find such a primitives, we can say pseudo-randomness is somehow useful in the quantum world. So thank you for your attention.
Thank you very much for your talk. Does anybody have any questions?
Thank you for the talk. And your approach is based on unpredictable state generators, right? So in this case, how do you ensure that repeatability of the states when you're generating unpredictable states, right? How you're ensuring the repeatability of the state is means it is not repeating the previous state or something like that.
Sorry, could you say again?
See, yours is based on unpredictable state generators, right?
Yes.
So how are you ensuring the repeatability of states? In the sense like it generated state 1 now, the next time also it is generating state 1. So how are you ensuring that it is not repeating these things?
So I'm not so understand your question, so could you say more?
See, yours is based on unpredictable, right?
Sorry?
Unpredictable state generators.
Yes.
So I'm based on that, the input is given to the state generator, so I'm getting a state, say X. Next time when it is, when I'm giving this input, if it is generating randomly, I'm giving the input, how I'm ensuring that the randomness of the input is ensured so that it will not generate the state X again?
Sorry, I'm not sure.
Initial and initial boundary conditions, how are you taking care?
Yeah. Sorry, I'm not sure.
Are there any other questions? If so, I'll ask a final question. So in your last slide, you listed as an open problem separating PRFSGs and UPSGs.
Yeah.
So to me, that implies you think they're separate. Can you explain a little bit of intuition why, if that's true, if you do think they're separate classes and they're more likely to be separated than UPSGs implying PRFSGs, can you explain why you think that?
So I don't have any idea to separate them. Yeah, but if we can separate them, we can say our take-home message is more stronger.
Right. Okay. Thank you.
Yeah.
Question.
Thank you for nice talk. So, do you have any concrete candidates for the UPSGs?
Sorry?
Do you have any concrete candidates for the UPSG?
For the complete?
Candidates.
Candidate. So if for example, PRFSCs is implied by a post-quantum one-way function. So therefore, if there exists post-quantum one-way function, UPSCs also exist.
Ah, okay. Thank you.
Question.
Yeah, it's directly not related to this talk, But on the general things on quantum cryptography, I just need to have some views on the possibility and future of quantum memory actually, because it's not directly to the speaker. I think anyone can answer it. Quantum memory, how far it is yet, because people are working on it, because we can store the quantum state for some time, maybe right now, maybe feasible for few seconds or few minutes, but how far it is feasible actually.
Yeah, so
Anybody, it's like general question.
yeah, so this is not so practical one because if so for practical we can it's sufficient to use post-quantum or function or other post-quantum cryptography. So this is only theoretical interesting.
We have a minute. Does anybody from the audience want to comment on that? Sorry for the unorthodox.
So it's not a comment on this question, but a comment on the previous question about unpredictability. So just a thought that in the classically when we say unpredictable, so that means it is indistinguishable from uniform distribution, right? So I guess in the quantum domain, when you are talking about unpredictable states, so even if the state is repeated, it will be with uniform probability. So it does not matter because without measuring and destroying the state, you won't be able to know whether it has been duplicated or not. So that's a comment on the first question.
Thanks.
Are there any other questions? All right, well, let's thank the speaker again. And thank you all for coming. I believe the next part of the conference is a coffee break. So please enjoy your sweets and coffee.